first order system. So this is a refresh what we've been talking about. For first order system, this is a transfer function that we have, and we say tau is time constant. This will be the most important coefficient you need to know for such kind of a transfer function, because we will need to know the transient response of this specific system using this constant. So if we know my horizontal axis is time, and my vertical axis is my magnitude. So based on final value theorem over here, you know eventually this is going to be what? 1. Right? So we know it's going to approximate to this line with some kind of curve. So if you draw a line, tau, 2 tau, 3 tau, 4 tau. What are we going to have? Over here, if the time has passed for one time constant, it will go to 68%. For 2 tau, it's going to be around 86%. For 3 tau, it's going to be here 95%. 4 tau is going to be 98%. So if we draw a curve over here, it's going to approximate in this way. So with this specific configuration, we know if you have first order system, there is no overshoot. That's the behavior of first order system. So when we have this kind of things, we know it's going to be approximate from 0 to 1 after 4 tau. Most of the time, if you look into your textbook, it's going to be either 4 tau or 3 tau. If you are using data Franklin, the textbook you're using right now, it's going to be 4 tau, 5%. If you are using NIS textbook, they use 3 tau. I think Benjamin Guo, BC Guo, I think it's using 3 tau as well. But depending on which textbook you're using, you're going to adopt different time constant. I know some, the other day there is one student come to my office and asked me some specific question for graduate school entrance exam. Depending on which textbook you're using, the solving procedure might be a little bit different. But normally, if you take 4 tau, specify that in your solving procedures, it should be fine. Okay? So this is the first order system. Today we're going to talk about second order system. So for second order system, it's going to be a little bit different. For a second order system, that is of course my output over input. If you take a look at this one, sometimes you're going to have a form like this. You got a coefficient in the numerator, you got your polynomial in your denominator. We do not consider we have 0 on top of here. We only consider this is a constant and this is constant. We are talking about a generic second order system. So when you have this kind of second order system, keep in mind the coefficient over here is b. It's going to be b over here. Why is that? Because we want to have the output, the result of this output going to be 1 eventually. Does that make sense? Because we say we want to apply finite value theorem and try to push that into 1. So if you multiply this coefficient, this transfer function by a k transfer function gain, then it's going to increase to any value you want to have. So it doesn't really a big deal for this kind of things. But keep in mind when you do the analysis, this b and this is b. Okay, that is the first thing. Second thing, when we have this kind of format, this doesn't really give us a whole lot of physical meaning because those coefficients can be anything we want to have. But when we are having a mechanical system, those coefficients is actually corresponding to some specific mechanical properties. They are going to be represented as okay, this is omega, not W. This is omega, and this is zeta. So when we have zeta, this is my damping ratio. We have omega n, that is going to be my natural frequency. Okay, normally we would like to have our damping ratio greater than 0, smaller than 1. We do this for a reason, because if your damping ratio is greater than 1, and you are using the solving procedure to solve this second order system, you're going to find out when this one is greater than 1, you're going to find out this is actually a combination of two first order systems. Okay? So when you have first order system, are you going to use second order system to do the analysis? No, because if we can decouple this one into two first order systems, we use this one. That will be easier. Does it make sense? We do not want to use second order system equation to analyze the combination of two first order systems. It doesn't make sense, and it will make your calculation procedure way longer. So we don't want to do that. But if we are talking about the damping ratio smaller than 1 and greater than 0, then there is something we need to do the analysis. Another information you guys need to have is this is damping ratio. We talk about when we have a mechanical system, you apply a force over here. Damping can be a damper over here or the friction over here. Right? So when we have friction, that is going to be corresponding to my damping ratio. My question is, can we have negative damping ratio? Yes or no? The question can be think as, are we going to have negative frequency force? Friction force? No, right? So this one over here always needs to be greater than 0. Make sense? So when we have this kind of things, we can do analysis over here. My characteristic equation of this transfer function is going to be s squared plus 2 zeta omega n s plus omega n squared. And we say this is going to be second order equation, so it means that I'm going to have poles located at s equals to negative . Okay. No, this is a formula, but you can solve this one manually because you know this one is going to be right? You guys done this in middle school. So if we have this one greater than 0, we're going to have positive output of this square root calculation. But since we have damping ratio smaller than 1, normally it's going to be smaller than 0 over here, which means this part is going to be a complex number. So when this one has a complex number, we need to use J to represent everything. And this is going to be a formula or the corresponding poles for my second order equation. Very straightforward, right? So we will need to calculate, first thing, what is our pole going to be located? This is important because we're going to use this part to do a little bit of analysis when we are designing our controller. And when we are having this kind of things over here, we can kind of understand how my damping ratio and how my natural frequency going to affect my system response. This is the first thing we're going to do. Pulse. Second thing we want to know is overshoot. Overshoot. Normally we would like to use percentage. This one over here is going to be the 100. Peak. This is peak output. Minus steady state output divided by steady. Steady state. So if we get this one over here, this is actually some kind of percentage because I multiply everything by 100. So eventually what we're going to do is exponential something like this. Okay, I know so far this doesn't make sense to you, but if I put everything in this format, you're going to understand what I'm talking about. Just keep in mind, there are three things we need to know. One is pulse, the other one is overshoot. There is a third one, I'm going to write it down. Those three things are important when we try to analyze second order equations, okay, physical. The third one is settling. So, in the first order equation, what is important? Time constant. Because when we have time constant, we know 68%, we know 86%, we know 95%, we know 98%. And those things is going to be valid over here. Because it is important that we need to specify what is a 2% error, 5% error, because we need to have those information to determine whether our system is stable or in a steady state status. You cannot just say, okay, I wanna do things in 2 seconds, and 2 seconds is going to be my settling time. What does that mean? It is going to have some similar stuff corresponding to the first order system. The definition is going to be 98. I'm going to use 98%. That is going to be TS settling time equals to 4 tau, which is similar to what we have in the first order equation. And this is going to be 4 divided by theta multiplied by omega n, which means if you try to analyze this one over here, 1 over zeta omega n is going to be corresponding to my time constant in the first order equation. Does it make sense? So if I want to have 2% error, it's going to be 4 tau. If you want to have 5% error, instead of using 4, what should I use? 3, right. If you want to have 99%, this one over here becomes 5. Okay? So, what does that going to look like? I might not do a good job drawing, but the figure is in your notes. Just take a look at the notes, okay? So, of course, this is my transfer function. What I want to have is the output equals to 1. So I'll have this one is going, when you look at this, the second order equation, we do one homework. No, we do one problem in your test, right? So if you have something like this, and you use inverse Laplace transform, let this one go back to its time series. What kind of function are you going to look at? Cosine and sine, right? But when we have cosine and sine, there is one specific term involved in this guy, which is exponential. When you have exponential, what does that mean? It means that it's going to be decay and approach to a certain value, right? When you have cosine and sine, what does that mean? It means that it's going to be oscillating. And this oscillating, the magnitude is going to be 3 because you have exponential term in front of it. So the magnitude over here is going to be smaller and smaller until it reaches to its steady state. Does that make sense to everybody? I mean, physically, is that understandable? Any questions so far? You need to understand this one precisely because that will help you to understand the system we're going to deal with in the future. Any question? No? Okay. So when we are doing things over here, this point over here is my overage. So this is my 1. Steady state, I want everything to be 1 output. But since this one is oscillating and this is a second order system, we have no choice but have some kind of overshoot over here. So how much percentage we're dealing with over here is something we can calculate based on the equation over here. So we need to know what is my peak value minus the steady state output divided by 1. So this is going to be my overshoot. Okay, and let's say if this one over here is 2%. The time over here is going to be my time constant. There are other things in your textbook, which is your rise time, peak time, delay time. Those things, well, it's not that important, but you can find a definition over here. Some textbook include this part in the text, but I think the textbook you guys are using does not have that one. So this part over here, I actually copied them down from another textbook. So those are just definitions. You will need to know what's going on. And when people are talking about TR, TP, TD, what does that mean? But that's just a definition. You don't need to memorize those kind of things. Just know where to look it up. That will be good enough. Okay? Any questions so far? No? Okay. Then we have something we need to discuss. One thing more important is damping ratio and overshoot. Those two things are connected. We're going to use another color. So overshoot is highly dependent on what is your damping ratio is going to be. So go back to the equation we have in your test. I think it's going to be I think this is problem 4, if I'm correct. So the exponential term over here is what? Decay. Cosine and sine over here is what? Oscillating. So let me ask you a question. If this one over here is gone, and we just have one thing over here, what kind of output we're going to look at? Will my magnitude become smaller when time goes to infinite? No, right? The magnitude remains the same all the time. So, what happened to make everything become smaller? The exponential term, right? When we have exponential term, it's going to be corresponding to zeta. So, if your zeta is small, in this case, my zeta is 0. which means it's going to oscillate all the time, and it won't stop. But if my damping ratio increase, it means that this one is the exponential term over here is going to be changed as well. So when we have those kind of things start to increase, it means that I'm going to start to shrink my magnitude of oscillation. Does it make sense? So when my damping ratio becomes larger and larger, what happens? The magnitude of the oscillation becomes smaller and smaller. So if I have my damping ratio equals to 0.707, that will be in your next page. When damping ratio start to be changed, when damping ratio start to change, what kind of result we're going to have? So it's going to be something like this. This damping ratio is specific. We would like to keep this one all the time because the overshoot in this case is 5% when your damping ratio equals 0.707. 0.7 is fine. But when we say it's 5%, this is acceptable because when we are talking about steady state, the error is normally either 5% or 2%. Does it make sense? So it means that if my damping ratio is small, my magnitude is going to be large. If my damping ratio is high, it will become smaller. If your damping ratio is greater than, I would say, 0.8, we no longer have overshoot. So you might ask me, so since we don't have any overshoot, why not we use higher damping ratio? 1. If your damping ratio is greater than 1, it becomes first order system, a combination of first order systems. That is going to be the other analysis, so we don't consider that part because since they are first order system, we just use that part to do analysis. That's not a big deal. Secondly is, we're talking about settling time. Based on what I'm drawing over here, which one has faster response? Damping ratio smaller or damping ratio larger? Smaller. So we want to have that to be fast response. However, if the damping ratio is way too small, we got large overshoot. If my damping ratio is way too big, though we don't have any overshoot, but the response time is way too long. So we need to balance both of them. So in the textbook of Ogata Franklin, we use 0.707. For NIST textbook, you are not using that one. It suggests damping ratio to be 0.5. But I don't like that number. So when you are doing the calculation, most of the time use 0.707. Does that make sense? The 0.707 has its physical meaning. The overshoot is small, around 5%. The settling time is okay. Compared to 0.5, it's not going to be too slow. Any question? Okay. Now, based on what we're talking about here, we're going to do a little bit further. Okay, so that is time series because this one over here is time. Now, we are not going to use that one because when you are doing analysis, doing controller design, we are not designing using time domain. We are going to design everything in terms of estimate. So what that mean is I'm going to draw this like this. we're going to put pole locations on this plot. So the two S's over here is no longer time and magnitude. This becomes real part of your pole, imaginary part of your pole. When we are doing something like this, look at this one over here. My second order system, I have negative zeta omega n plus minus j square root of 1 minus zeta squared multiplied by omega n. Right? So when we are doing something like this, the real part is going to be this one. Imaginary part is going to be okay. So I'm just put that into xy position. This is my horizontal, this is my vertical. So if I do something like that, you get all the numbers over here. This is my pole location. Any questions so far? So how do we know this one over here? So the angle, you're going to find, if you put this square plus this square, you're going to get omega n as a distance from the origin. Does it make sense? Because one is sine, the other one is cosine. Real part is cosine, imaginary part is sine. I think you guys know this in calculus, right? So if you square this number, and take the square root of the combination, it's going to be omega n. So if you do the calculation, you're going to find the angle over here is going to be something like this. Okay? So if your damping ratio changes value from 0 to 1, what happens? This angle is going to be changed. If you do the calculation, we're going to find if you increase your damping ratio from smaller one to bigger one, this omega n thing is going to get close to this one. So does it make sense to everybody? Because if this one is 0.707, you take 1 minus 0.707 squared, you're going to get 0.707. 0.707 squared is what? 0.5. Right? So if you have 45 degrees, it means that it's going to be zeta equals to 0.707. So what does that mean? Again, so it means that if they will tell you some index. Okay, so if you have 45 degrees over here, you draw the line in the S domain. You're going to find in this blue region, I have my damping ratio smaller than 0.707, and this one over here is greater than 0.707. What does that tell you? It tells you overshoot. If you have your pole locations in this region, it doesn't matter where you locate it. The overshoot is going to be greater than 5%. If your damping ratio is smaller than this region, is in this region over here, it means that your damping ratio is your overshoot is going to be less than 5%. That is going to be one important thing we're going to use. Secondly, you look at this one. Time constant or settling time. What does that tell you? 4 over zeta omega n. So if you look at this one over here, what does that tell you? This number over here tells you how fast your system can respond, right? Because it's based on my settling. So if you put things over here saying this one is my negative zeta omega n, it tells you how fast your system is going to be respond to your specification, which means if you draw a line over here, if you put your pole in the left hand side of the thing, your system will be fast enough to catch everything with overshoot less than 5%. If you put your system within the yellow region over here, it's too slow, though the overshoot is going to be less than 5%. If you put your region over here, it means that your overshoot is going to be greater than 5%. Sometimes we don't want to operate our system within those blue regions and within this yellow regions over here because this part is too slow. This part over here, the overshoot is too huge. Okay? Any question? No? If not, then I do. So we talk about the damping ratio. If it's going to be smaller than 0.7, it's going to be in this region. So what if my damping ratio equals to 0 exactly? Where are my poles going to be located? Zeta equals to 0. Take a look over the poles.
Imagery axis.
It's going to be over here. Right? Okay. Next question. If I have my poles over here, what happened to my system? Unstable. Very good. It's going to be unstable because instead of converge your system into a constant, this one over here, your system is going to be diverged. Right? And when we say our system is divergent, it means that my system is not stable. So if your damping ratio is 0 or you have your pole right located on this line, your system is critically stable. So this line critically stable because the magnitude never reduces. It just remains the same magnitude. Since it's sine and cosine, if you have poles located along this line. If your system has damping ratio, it becomes stable, so you're going to have everything on this side, and when your system is greater than 0, it's going to be on this side and make everything unstable. But if you want to be more specific, how much overshoot you are expecting, how fast your system is going to be respond, you need to draw those kind of regions in so that you understand where are you located and how system is going to respond to your specification. That is how we use second order system to do analysis. Any question? The discussion is actually in your notes. I've just put everything, explain everything, all of it. So I have 3 closed loop system, and I'm giving you different kind of things, and you need to find out what's going on over here. So I give you GH. Normally my system is going to be do I give you? I give you GH. Means this is not the relationship between output and input. It's the combination of this one and this one. That is important because my y over r is going to be 1 plus GH. So when you are doing, keep in mind when you are doing the analysis, we are not analyzing in the coefficient of this one and this one. We are analyze the system as a system, which means you will need to get the closed loop transfer function before you start to do the calculation. Does that make sense? So when we have this one over here, my characteristic equation is going to be s squared plus 2s plus 10, because it is, I'm going to use this one over here, this one over this one, and that also leads to a thing I need to talk about your test. Next time when you are doing the test, and write down the transfer function, please simplify everything to a simplest representation, so I won't take points. If you give me a lot of coefficient, I need to do a calculation, that take points. Because again, I'm lazy. If you make me to calculate, you pay. Okay? So the characteristic equation over here becomes s squared plus 2s plus 10. So when we have this one over here, we start to do the calculation, which is so with this one spacebar over here, my omega n is going to be square root of 10, which is can anybody do a calculation over here? I think it's 3 point something, 3.16. I think it's this one, but I'm not positive. Right? Okay. So the natural frequency is going to be 3.6 radians per second. One thing important to you guys is this 1 hertz. Is this unit hertz? Yes. Yes? No. It's not. Okay? If you want to use hertz, you need to divide this number by 2 pi. This is radians. Hertz is 1 over s. So this is radians, so you need to divide it by 2 pi. Okay? So when you are talking about frequency, there are 2 representations. One is radians per second, the other one is hertz. Normally, when you are doing calculations theoretically, we are using radians per second, not hertz. When you need to do hertz, you need to do a little bit approximate. The reason we're doing this is because when we are doing radians per second, it becomes periodical from 0 to 2 pi. Hertz doesn't have that kind of character. Okay? And when we are doing something like this, we know, which means, since we know my omega n over here, then my damping ratio becomes this one. So there are a few things I'm asking over here. Find the damping ratio, natural frequency, settling time, and peak overshoot for unit step input. So the next thing we want to do is settling time. We just adopt formula. So in order to achieve 2% steady state error, you need to take 4 seconds. Next thing we want to talk about is percentage overshoot. Again, this one over here, you will need to use formula. Since I have my data spacebar, just adopt this formula, you're going to find out the overshoot is 35.1%. And that is going to be my answers for part A. I'm not going to have time for part B and part C, but this is, when you look at the second order system, you got the characteristic equation. You should be able to identify what is the natural frequency, what is your Debye ratio, and based on those two properties, we can know what is my settling time and how much overshoot I'm expecting in my system. Is that clear? Everybody understand what we're talking about over here? Any question? The other important thing over here is when you get the equation given in the problem statement, you need to be careful because sometimes it's given you the transfer function of individual blocks. In that case, you will need to identify what is your characteristic equation. If I'm giving you the transfer function between y and r directly, then you don't need to worry about this part. You just take the denominator, and that is going to be your characteristic equation, and you can do those kind of calculations directly from the equation. Okay, so depending on what I'm giving you, you will need to do those kind of analysis accordingly. Is that clear? Everybody understand what I'm talking about? Any questions before I let you guys go? No? Okay, we're not going to have homework this weekend, so enjoy your weekend.